But maybe wait 10 seconds. Okay, so thanks for coming. So this week we're pleased to have Dadush from CWR and Utrecht. He was visiting Japan for the sabbatical. We'll talk about LP, right?
Yeah.
Yeah, please.
Yeah, so thank you so much for the introduction, and sorry that I can't spell math, but we continue. So this is joint work with my former postdoc, Cedric Coe, Benton Natura, who's at Columbia, Neil Oliver at LSE, and Allamigeon Végh, who's now moved to Bonn. Okay, so this talk is going to be about solving a specific class of linear programs in what's called strongly polynomial time. So I should explain what those terms mean. And I will give you a little bit of background on the types of linear programs. These are ones where you use at most two variables per inequality. And we will switch to a dual view, which relates to minimum cost generalized flow, so I'll have to define that. And then I will tell you about a method, but I will mostly tell you about the analysis of this method, which is actually very distinct from the method itself. And I will try and explain why that is a little bit later. Okay, so linear programming in general, we're looking at the problem of solving a linear optimization problem. So you want to sort of minimize some linear function over something that's defined by some equations and linear inequalities. And here we have on the left what's called standard form linear program. And in this context, I guess if I was really minimizing, somehow I would end up here if this was the objective, but that's such is life. And then just for your general knowledge, we won't go too deeply into this. Sort of every linear program has a dual linear program where the solutions to the dual give you lower bounds on the value of the primal. And as long as, I don't know, both sides are feasible, they have the same value. Okay, so this is like some general duality principle. And our goal is going to be to solve linear programs exactly and understand when this is sort of easier or harder to do. And linear programming in general is quite old. I mean, this was, I would say, like, the modern theory that relates to optimization was started by Kantorovich in like the 1930s for some Soviet production planning. And you know, many economists and whatnot picked up on this. And it's something that's used all over the place today, you know, for all sorts of logistics problems. Okay. So the kinds of algorithms that one can think of are, if you want to actually solve this problem, you can think of what you would usually hope to be a polynomial time algorithm. And a polynomial time algorithm is something that runs in time that's polynomial in the size of the input. And if I give you, you know, your input data, which is a constraint matrix, your right-hand side, your objective, then the size of the input, generically speaking, should include like the size it takes to actually write down the coefficients. Right? So maybe these coefficients of A, B, and C are maybe very large rational numbers, this kind of stuff. So it might take a lot of bits to write this down, more than just, you know, n times n, right? Kind of stuff, more than just the dimension of the problem. So a polynomial time algorithm should in general be allowed to run in time that's polynomial in the size of the input. Indeed, I mean, it actually took quite a while for people to even find any polynomial time algorithm for this problem, but perhaps many of you or some of you know some of the sort of classical methods in the context of optimization that have been applied to this. The ellipsoid method is something that's used all over in combinatorial optimization. And this was first applied at the end of the 70s to show that solving or linear programming is in fact in P. And for us, we're going to be interested in a different class of method, which are called interior point methods. And we'll mostly be interested, as you'll see later, in the geometry of these methods. The algorithm I will not talk so much about today. And these are two examples, or sort of most important examples for now, of polynomial time algorithms. But, oh yeah, and then the most combinatorial method, which is also still very popular use today, is this simplex method, which maybe some of you have heard of. And this is a more combinatorial thing where you kind of walk over the edges of your feasible region, your polytope, until you get to an optimal solution, taking one step at a time in an improving method. Okay, good. All right, so that's the the first two were polynomial. The simplex method, we actually don't know that it's polynomial. But I'm going to introduce another concept, which is a refinement on polynomial time, that was introduced basically because people wanted to see more combinatorial kind of algorithms for linear programming that would take take a number of steps that was proportional to the number of variables and inequalities in the system. And the previous, or all the algorithms that we know, do require a sort of number of iterations that depends on how complicated the coefficients are. Okay, so like if you're thinking of a graph problem, you would want, or like a flow type problem, you would want an algorithm that depends on the number of edges and nodes, not necessarily like, how bad the weights are in the coefficient, in the objective. So this is what motivated the definition of strongly polynomial. So what you want is a method that takes a number of say basic steps in some sense, or number of basic operations that is polynomial in just the dimensions of the problem. And the basic operations here that we're going to think of are just basic arithmetic. So you can think like for these operations, I'm going to sort of charge you a cost of 1, and I'm not going to care like how complicated it is on a bit level to like multiply or add your numbers together. But then there's also a technical condition, which is that the numbers in your method should not explode, and that corresponds to having bounded space. Okay, and like a question that was sort of formally stated by Natura and Végh in the early 80s and was like popularized by Stephen Smale in the Problems for the 21st Century is like, is there a strongly polynomial algorithm for solving linear programming? And you can actually, in this context, even if you forget the second bullet, so just give me any method whatsoever that just uses a small number of additions, multiplications, divisions, we have no idea. Okay? We always, somehow all the algorithms seem to require some dependence on the complexity of the coefficients. So now there are many, many different types of linear programs, and here's just a picture to give you a sort of classification. So we have linear programs, so many of like your favorite combinatorial problems, such as shortest path on a graph, or like finding a perfect matching in a bipartite graph, or finding a maximum flow in a flow network. All of these things can be written as linear programs. Of course, we have like more specialized algorithms than just general linear programming algorithms to solve these problems. And these indeed can be solved in strongly polynomial time, like shortest path. We know Dijkstra's algorithm. You can solve shortest path in essentially linear time. There are sort of wider classes. the first class that was actually looked at by Nimrod Megiddo in his paper where he defined sort of strongly polynomial time is that he showed if you just want to find a feasible solution to a linear program where every inequality in your linear program like is supported by at most two variables, he showed that this you could do in strongly polynomial time. And there are sort of other versions. One is like somehow related to the feasibility of dual programs here, which is a sort of generalization of maximum flow. And this was shown to be strongly polynomially solvable much later, so in like 2013 by Latside. And it is worth noting that like so these are the things that before our work, or at least this thing, before our work we didn't know how to solve the optimization version of linear programs with two variables for inequality. The MDPs are Markov decision processes, so this is, yeah, let's not worry too much about what these are because I won't talk about them. But it is worth noting that if you're like trying to like parameterize in your programs by how many variables appear in each inequality, like the moment you go to linear programs with 3 variables per inequality, and you essentially are able to model all linear programs in the same way as like if you can solve, you can reduce like let's say k-sat to 3-sat, this kind of thing. So basically if you can solve LPs with at most 3 variables per inequality in strongly polynomial time, you can solve all linear programs. So there's like a natural barrier between 2 and 3. And it's just like the simple thing of taking, you know, an inequality that has more variables and writing it as 2 inequalities where you aggregate some of the variables. And,
how big is the blow up, like when you reduce this?
I think it's like logarithmic or something, or maybe
like number of variables should go up, right?
Yeah, yes, but not by much.
Uh-huh.
Okay, I'm not going to guess, but probably you get like log n more variables or something like this, or n times more variables. Something.
And that's true for both feasibility and the actual optimization.
Yes. You can. I mean, it's just like you rewrite the feasible region, and you know, if you rewrite the feasible region, then you know there's a one-to-one way of changing the objective function. Yeah. Okay. So what we did is sort of we brought the optimization version of linear programs with 2 variables per inequality into the fold, and so I will tell you more about that. So one first thing that you can do sort of so Hochbaum showed that there's sort of a very simple transformation that allows you to write like any linear program in 2 variables per inequality by sort of doubling the number of variables like into this form. So where like every inequality has exactly 2 variables and one of them has a positive coefficient and the other coefficient is -1. This is like a sort of simple doubling trick. So these guys, perhaps it's like not the easiest thing to interpret what they might be. And for people like me who like things like flows, which perhaps are a bit easier to understand, it turns out that you can sort of go to the dual program. And in the dual program, you will see a flow structure. And you know, these sort of pairs of variables will sort of naturally correspond to like a graph, you know, with edges associated with I and j, and we'll be able to think about a sort of generalization of flow on these graphs. So what are we going to be looking at? So the dual of this program can be expressed sort of as follows. And essentially, this is sort of if you didn't have these like funny like gamma multipliers, this would exactly be like a sort of minimum cost network flow problem. So this would be like, at every vertex of the graph, you want sort of this amount of sort of net flow, and subject to having this amount of net flow in every vertex, you want to sort of minimize the cost of the flow. Okay. Now, that would be sort of regular flow. In this context, where we have these funny multipliers, which are called gains, you have a slight generalization of this, or well, a non-trivial generalization of this. And what's happening is that, sort of in regular flow, if I send sort of 20 units of flow like out of an arc at the beginning, like on the other side of the arc, 20 units of flow would arrive. Right? So I send 20 units out, 20 units arrive. In the generalized flow context, every arc has this gain factor gamma. In this case, it's 1/2, which says that if I send 20 units out at the beginning of the arc, like only half of that amount arrives to the other side. So the other half, like I don't know, falls out of the network perhaps. But these gains can also be like bigger than 1. So twice the amount of flow could arrive on the other side. But sort of other than this sort of arc-specific gain factors, it is exactly a flow problem. Okay? And so these things, they're useful. You can think of them as like, if the gains are all less than 1, you can think of like sending flow on leaky pipes. But you can also think of like currency exchange markets, like maybe this is the value in dollars and this is the value in won. And so on and so forth. So you can actually model quite a few things this way. Good. So our like all of our analysis is mainly focused on the sort of flow viewpoint, but our algorithms are sort of fully primal-dual. So we both simultaneously solve the primal problem and the dual problem. So it sort of doesn't matter that I'm stating this for generalized flow. And we do show that this problem can actually be solved in strongly polynomial time, the optimization version for minimum cost generalized flow. Okay. And so as I mentioned, this is going to be, the algorithm is going to be one of these interior point methods. I'm not going to, as I said, actually describe the algorithm. I'm just going to describe the sort of very vague geometry and the relevant parts of it that are needed to sort of bound the number of iterations of the method. Okay? Good. So the two concepts I want to get through are sort of a very, very high level view of what interior point methods try and do. And I'm going to sort of abstract the most relevant property of them. And that will get us to a complexity measure, which we call straight line complexity. And the whole goal will be to show that for the LPs that come from minimum cost generalized flow or the dual, that this complexity measure is small. Okay. Good. So what do interior point methods do? So essentially, what they try and do is they try and model this like optimization problem over like a polytope as like a sequence of continuous optimization problems. And what they try and do is, instead of just having the boundary as it is here, which is kind of a not very smooth object, right? It's got all these kinks on it. They're going to like replace the boundary, but what you call a barrier, and that. So the boundary here is sort of in this context corresponds to the fact that you should be in this linear subspace. So this is like the flow subspace, the generalized flow subspace that satisfies the net flow constraints at every vertex, such that the flow is also non-negative on every arc. So the boundary sort of is encoded by the non-negativities here. And what happens in the context of interior point methods is we encode this boundary by essentially penalizing you for getting close to it. Okay, and we put that in the objective. So this minus log term, which is called appropriately the logarithmic barrier, explodes if you get close to the boundary. It'll go minus log of x as x goes to 0 from the positive side, will go to infinity. So it'll say, like, please stay away from the boundary. But now when you do this, this is like a very nice and smooth, like, optimization problem. And your freedom here is to toggle, like, how much force you put on the boundary, which corresponds to putting a larger multiplier, mu, like inside the objective function. And the idea is that if you look at the sort of sequence of minimizers that you get for these optimization problems, so which are indexed by how much force you put on the boundary, like on the barrier, like what the multiplier is on the barrier, as you sort of decrease the weight of the barrier, you're allowing the solutions to get closer and closer and closer to the boundary. And eventually you will converge to the optimal solution. Okay, so you'll sort of trace some path through the interior of the feasible region, assuming the feasible region has an interior, which we're always going to be assuming. And it'll actually trace this very nice continuous path that goes all the way to an optimal solution. All right, so this is just like, this is going to remain relatively vague. So, I mean, we're not going to go into huge amounts of detail in trying to understand this, but are there like any generic questions so far about what's going on with these things? No. Okay. Good. So what interior point methods do is that, sort of this path is kind of very nice. They can't, you cannot compute the points on this path exactly. That's like impossible. But what you can do is sort of try and follow this path like approximately. And what will be important is that you'll sort of always have like a lot of space around you to move towards opt when you're following this trajectory. Like it's kind of the most interior trajectory, one of the most interior trajectories you can find that actually guides you all the way to opt. Yes?
So is there like benefit of like computing the minimizer with the penalty compared to the computing it without the penalty?
Yeah, I mean, with the penalty, basically what happens is you get like a unique solution, and like these solutions are like linked to each other via this like very nice continuous path. So it's sort of like, I mean, if you don't have it, then immediately, I mean, maybe there's a huge optimal phase, but often, like, let's say you can create a system where you add a few extra variables, and you can sort of start in like the very middle of your polyhedron in a sort of like higher dimensional space. This is like from phase 0 problem. And then you would like a continuous path that like interpolates between your starting point and where you end, and this can allow you to do that. Right. But there will be like other benefits that I will mention in a second. Yeah. Okay. Good. So we want to follow this path. That is the general story. So what is like useful, or what's really going on in terms of sort of geometrically? What is this path like achieving? Maybe is the right way. And I should mention that there are many different types of interior point methods that use different barriers. Like the logarithmic barrier is not the only one, but they will all like fit inside this framework. And so what am I going to suggest here? So first, it turns out that you can parameterize this path in terms of the optimality gap. So basically, like this path is like always improving in the objective. So it's not a big jump to think that I can uniquely parameterize points on this path by the optimality gap. So let's do that. And now you can ask, like, what is special about, a point on the path? What exactly is it trying to achieve? And it turns out that points on the path are basically as deep inside the feasible region as they could possibly be, subject to having the objective value that they have. Okay, so what does that mean? What we can think of is, what does it mean to be deep inside? So deep inside sort of says, okay, let me look at like every inequality that we have here. So for example, I can look at this inequality, like the fact that I should be above this thing. And I can say, okay, if I want to have like objective value sort of better than this point, so that corresponds to this part of the feasible region, like how far from this constraint can I get? Okay, and okay, in this picture you can see that like the farthest away point with respect to this constraint is all the way at the top. But I can look at this from all different constraints, like how far can I be from this constraint? And that's going to be sort of all the way here. And I can do that for like every single inequality. And what will happen is that this point on the central path will be sort of within a factor, it turns out, at most n, away from having this like maximum possible slack. So what you can think is like as I'm like moving this like hyperplane over, these points, or this particular point in this case, is approximately as far away from all of the constraints as it could possibly be. So if you look at this inequality inside this hyperplane or inside this half space, the furthest point away is, I guess, also this one. In this context, if I look at this inequality, the furthest point away inside this part of the feasible region is this one. And like you can see that these ratios, like from here to here, are not very big. Okay, and that, it turns out, will be true for every inequality simultaneously. That's like how sort of these central paths encode being like as deep inside the feasible region as possible. And so you can actually like look at this by defining, like for what we call the maximum central path, which is a sort of combinatorial analog in our context of the central path, which exactly says given like a gap G, which this is your optimality gap, which will define the objective value, like we will compute for the ith inequality, like how far away from the ith inequality, in this context the inequalities are all of the form xi is greater than or equal to 0, how far away can I be from the ith inequality subject to a bound on the optimality gap? Okay, so this is exactly like how far I can be on the ith constraint subject to having optimality gap 5 or 10 or whatever. I plug that gap into here. It tells me how big the slack on the ith inequality can be. And what one can prove, and this I'm not going to prove here, is that the central path is always sort of pointwise upper bounded by the maximum central path, because the central path is going to be like a solution to these things. Right? So if I plug in like what is the central path point with gap precisely G, it will be a feasible solution to this program, and so all of the coordinates of the central path will be upper bounded by those of the max central path. But the reverse inequality is also true. Up to a factor, so actually here I'm thinking about flow, so the number of edges is m. So somehow you get this approximation factor. Okay, so this will be the key sense in which the central path is like super deep inside the feasible region at every point in time. Okay, so I'm not proving this, but this is like an important fact. So it sort of says that if you're just trying to look at like the very coarse geometry of the central path, then you might as well look at this combinatorial analog instead. All right, and that's will be helpful. So if you do that, what pictures do you get? So here I'm just like going to stare at one coordinate. You can think like the true LP is living somewhere off this plane, and we're just looking at like a projection onto this 2D plane, where one axis corresponds to the gap, which is, if you're thinking about the algorithm, the gap is sort of decreasing over time. And the other axis is how far am I away from the ith constraint. Okay? And now this max central path is going to be this top curve, and it's going to tell me how much slack can I get for a given upper bound on the gap G. The bottom is just a scaled down version. And what the previous inequality says is that the actual central path is sort of sandwiched in between these two things. Okay? So now if you think about like what an algorithm might do, like an algorithm, it turns out, is going to sort of give you an approximation of the central path. It turns out very naturally that most algorithms essentially at every iteration solve something like a linear system of equations and like go like straight in a direction that comes from some Newton system that they solve until they get like too far away from the central path, and then they kind of repeat. And so there's a very natural way in which the iterations of essentially every interior point method like can be decomposed into something that looks like piecewise linear segments, where each segment is like one iteration. You know, I'm going to go from here to there, and then I stop, and then I'm going to change direction, and then I'm going to go here, and so on and so forth. So a natural question that comes from this picture is that, okay, algorithmically, like you can think of the path followed by algorithms as being paths that like approximate the central path via piecewise linear curves. Okay, so now we know that the central path is sort of very well sandwiched by the max central path. So the algorithm also, in essence, approximates the max central path via a piecewise linear curve. So now you can ask, okay, if I give you an approximation factor, so the approximation factor here is like 1 over 4m, like how many pieces do I need of a piecewise linear function to get like let's say a gamma approximation of the entire max central path? Right? Or let's say, you know, if I feel like approximating from here to the end, I can just, you know, restrict this definition of the like complexity to that interval. So I'm looking at the minimum number of pieces of a piecewise linear function that approximates one coordinate of the maximum central path. Let's say, in between the range of gap being 0, which is like where I want to end up, and perhaps my starting point. Okay, that's a natural notion of complexity. And sort of by the picture, this complexity notion, if I make my approximation factor small enough, will actually be a lower bound on the number of iterations of any algorithm. Okay, because the algorithms actually produce these curves. Okay. So that's essentially what this says, is that sort of all algorithms, natural algorithms that follow central paths, in fact produce nice piecewise linear approximations of the max central path, and hence their number of iterations is going to be lower bounded by, you know, how many pieces any such approximation must have. All right. So this gives you a natural lower bound, and it turns out that this is also up to like strongly polynomial factors an upper bound. so this is the method I will not talk about. But it turns out that there is an interior point method such that the number of iterations that this method takes is essentially proportional to the sum of these kind of univariate straight line complexities for all of the inequalities one by one. Okay? So we both have like kind of from a coarse geometric perspective, like like a lower bound on the number of iterations of essentially any interior point method, and an upper bound that are like not too far off from each other. So if you want to prove like an iteration complexity bound, which will in turn at least prove that you don't need like too many iterations, which will turn into not too many arithmetic operations, because somehow like each iteration of this method is not too complicated. You will get a bound. So it suffices to sort of show that these straight line complexities are like bounded by a function of, say, the number of edges. Okay, this is what you need to do. Good. So really, like, so that was a previous paper where we kind of designed this method, this interior point method whose complexity can be controlled by, or the number of iterations can be controlled by straight line complexity. And the main thing that we did in this paper is actually show that this number is small if you're looking at minimum cost generalized flow. Okay, so whatever minimum cost generalized flow problem you have, if you're approximating the max central path with respect to an approximation factor that's roughly 1 over n, you only need this many pieces. Okay, and that, if you put it all together, that gives you a strongly polynomial upper bound. Okay, so now the question is, how the hell do you get this? Right. So now there is actually a connection to matroids. Maybe people like matroids. And so the key thing that will be important here will be the structure of the circuits of the sort of matrix A that defines the linear program. So what are circuits? So in our context, we're going to be moving inside the kernel of some matrix A, like all the movement directions are inside the kernel of some matrix A. And the circuits that we're going to be interested in are going to be sort of support minimal vectors inside the kernel. Right? Or you can think of the support of those vectors, perhaps matroid theoretically these are the correct things to call circuits, but we're going to associate the vectors themselves as circuits. So support minimal vectors. Now if you're looking at sort of network flow, which was what you got when you didn't have these funny like edge-specific gain factors, so the flow that leaves an edge at the beginning is the same as the amount of flow that arrives on the other side. Then the kernel is the set of circulations, and the circuits are precisely sort of directed cycles. Okay, so like if I send 1 unit of flow along a cycle, then like the net flow at every node is 0, and it turns out that these are like the support minimal elements in the kernel. Okay, so they're nice combinatorial objects. That's basically the perspective. And so what happens in generalized flow? So in generalized flow, you have these gain factors, and you have 2 different types of circuits, like one that actually is like the same circuits as before in disguise. So these are the circuits where like if I try and send the equivalent of like 1 unit of flow around the circuit or around the cycle, like the same amount of flow like comes back as what left. And that sort of corresponds to saying that like, as I go over here, I get like gamma of this edge amount of flow that arrives here, and then that gets multiplied by this next gamma when I send it over here, and so on and so forth. And so it should be that if this is really like a generalized circulation, that the amount that comes back here is the same as what left, which just says that the product of the gain factors should be 1. Okay, and these are called conservative cycles because they sort of conserve, the amount of flow. But then you have the more complicated objects, and these are called bicycles. Okay.
Now it's on.
Now it's on. All right, so these are called bicycles. And what do bicycles look like? It's basically, you'll have like a cycle here which like generates flow. So basically the product of the gains will be bigger than 1. So when I send the flow around the cycle, there'll be like some left over here. So I'm going to take it and I'm going to ship it down to another node. And then in this other node, there'll be like what's called a flow absorbing cycle, where the amount of flow that comes back is less than what I send out. And I can use that, this cycle, to cancel out the excess flow here. And I put those together and I get, like these are the basic building blocks, let's say, of elements inside the curve. So these are the 2 different types of circuits in the context of generalized flow. So what's the idea? So what we're going to try and do, I don't think I'm going to get apparently very far in this context in the next 9 minutes, but what is the high level idea? The high level idea is, we're going to try and approximate this max central path. We have to show that I only need like mn roughly pieces to approximate the whole thing. To do that, we're going to use like elementary functions to try and approximate pieces of it. And these functions are going to start from the left. Slightly confusing because like in an algorithm you imagine like going from right to left, like decreasing gap. In the analysis for understanding how complicated this stuff is, we're going to go in the opposite direction. So what you can think of is like this corresponds to the optimal solution, and I'm going to pick some direction to move in. And I'm going to sort of move in that direction as far as I can until I like hit some boundary of the feasible region, which may be like off the screen. And then once I hit the boundary of the feasible region, the sort of function will sort of flatten out. Okay? And this will give me like a curve that has 2 pieces that is indexed by the starting point, which is the optimal solution, and the direction that I'm moving. Okay? So we're going to try and find, so these are curves with 2 pieces. And we're going to try and find like a small number of these curves to approximate the whole thing. And circuits are going to be sort of great for us because it turns out that like I don't need to try like all possible directions if I want to get like a reasonable approximation. In fact, I only need to try directions that come from circuits. Okay, this is like a very, very useful fact. It's kind of related to things like, I don't know, flow decomposition into paths and cycles, but sort of generalized here, is that if I use only circuit directions, then if I take like the maximum of the curves that I get in this way, so I have like a curve for every single circuit, and I can think of, I'm trying to approximate this maximum central path, so I can just say, okay, well, let me just take the maximum over all possible circuit curves. This is actually not too far away from the top. Like the gap here is only going to be, in the worst case, 1 over m. All right? So it sort of suffices to look at these types of directions, because I'm only looking for a pretty coarse approximation anyway. And now what we're going to try and do is we're going to try and find like a small number of circuits such that the corresponding curves for those circuits do the job. Okay? And this will start to become combinatorial because now we're going to try and talk about like, oh, here is like a potential arbitrary circuit. But this circuit is worse than one in my collection, and so I can kick it out. Right? That's going to be a little bit the idea. And good. So as I said, the strategy in essence will be to find a small number of directions, which will turn out to be circuits, such that if I look at the maximum of all of the curves that I have in my family, they do the job for me. And each of these curves have like two pieces. So if the number of circuits I use is k, then this approximation has 2k pieces. So it's pretty direct comparison. Okay, so that's the plan. Okay, so just like pictorially, what we're going to try and do is we're going to try and show that I can find a small collection of circuits such that if I take any other circuit, one of the people in my already existing collection does like almost as good. And here I have a picture of just strictly doing better so that you get some sense. So here the circuit corresponding to F is going to do sort of strictly better than this guy because it's like above everywhere. And the way you should think about it is that, there are two parts to this thing. Like there's the flat part, which sort of corresponds to like how much flow maximum, what is the maximum amount of flow I can like get on the edge E in this direction before I like leave the feasible region. So that like corresponds to the top. And this sort of corresponds to like the, this part. Like the thing that's relevant is like how expensive is it to send sort of 1 unit of flow in this direction. So I want to send 1 unit of flow on E, and I'm like, how much am I going to pay for that in terms of cost? And so what you want is you want the cost of sending 1 unit of flow on E to be sort of smaller here than there, and you want the maximum amount of flow I can send using this direction to be more here than there. And so those are the sort of two things that you need to keep in mind. Okay. So those are the like two axes on which you need to compare two circuits by. Right, one is how much flow can they send on the arc E before like you leave the feasible region, and the other is like the cost per unit of flow. Okay. Good. So, let me see. Yeah, I'm not.
It's okay. I mean, you have 10 minutes. So.
Yeah. Okay. So then maybe I'll give you a little bit of a sense. So what we were trying to do is like build this small collection of circuits that sort of defeats all the other guys. And understanding these circuits directly is a bit too painful because they're like, these two cycles put together with the path. And so sort of combinatorially, they're made out of 3 pieces potentially. And so what we're just going to focus on is like one of the pieces in the context of this, which forms like the key. And the piece that we're going to think of is just a path in between 2 vertices. So we're going to think about like paths between S and T. Like we'll think of those as our circuits, even though they don't like live in circulation space. And what we're going to do is we're going to define our like object, like what we're trying to do, as sending sort of 1 unit of flow into T, right? So previously we were trying to send like flow on an edge, and now we're going to just think about sending flow into a vertex. Okay, so just it's a slightly different thing that we're going to do. So we're going to try and send like flow into a vertex, so precisely 1 unit of flow, in the cheapest possible way is one thing. So this will relate to cost being small, and so actually is that it? In the cheapest possible way? Yes, there are 2 things. So it's like in the cheapest possible way is one thing, and the other view is like like what fraction of the capacities am I using on this path? Right, like if I'm using a very large fraction of the capacities on this path, then sort of it means that if I wanted to send like more than 1 unit of flow, or well, yes, let's say more than 1 unit of flow, I would hit a capacity limit earlier. Okay, so those are the two axes. One is like how much total flow could I send like into this vertex without exceeding the capacities, and like what is the cost per unit of flow. And so I'm normalizing currently to just say I'm going to like send exactly 1 unit of flow. So this is good for like the cost version. And I'm also going to be worried about like what I'm doing to the capacities on the other arcs to see how much total flow I would be able to send. Okay. Yes. So we're actually it turns out for the purpose of like the domination argument, we can't only use paths. We have to use sort of walks, but we're going to use walks to dominate paths. So this will sort of there's a little bit of cheating, but don't worry about it. I mean, walks will be allowed to use edges more than once, and the cheating will happen in the sense that we basically every time a walk uses an edge, we're going to assume that it's fresh. So basically, it's like capacity will be, like reset to what it was originally. Okay, but we're not going to use arcs too many times, so it won't be a big problem. And so here are the kind of objects that we're looking at. So we're looking at two different like walk, or in this case path flows into T that send 1 unit into T. And we want to try and sort of build a small collection of these walk flows such that any path flow is dominated by one of them, which will mean that the walk flow will be cheaper, like in terms of sending 1 unit of flow into T, and we'll use like a smaller fraction of the capacities. Those are the sort of two things that we're looking for. And the question is like, how do we do this? Like, how do you build this collection? Right. So this is like restating the two things. We want like to build a small collection of walks that dominate all paths, essentially. And we're going to measure this like in terms of cost and in terms of how much flow they can send to the target. The only thing is that the cost we're going to measure in a sort of slightly funny way. Usually cost, you would imagine I should sum all the costs, like across all the arcs. That would usually be the notion of cost. And here I'm just going to look at only the most expensive arc. So I will declare the cost of the path to be like the most expensive arc it uses times the amount of flow it sends on that arc. For the fraction of capacity, this is like more or less what you would expect, modulo the fact that I'm allowing myself to replicate edges a few times. Good. So these are the two notions of domination. How are we going to build like a small collection of sort of dominating walks that beats all the paths? Good. So let me show you this. Okay, I think I will say just like a couple of words and then I'll stop. So the two things that we're going to pay attention to when we're looking at a walk or at a path, that's what we're really going to start with. We're going to start with paths and turn them into walks, is we're going to look at a combinatorial signature that will allow us to sort of like each signature at the end will have like one walk associated with it that will beat everything with the same signature. That's basically the idea. And there will only be a small number of distinct signatures. And the signatures will relate to the sort of natural things coming from what we need for domination. The signature will relate to like the most expensive arc from the perspective of cost, and the most dangerous arc from the perspective of violation of capacity. So there are two objects that we need to pay attention to. The most expensive arc that's the cost bottleneck, and the like arc for which I use the largest fraction of capacity, that's the flow bottleneck. So good. Like here I guess you have one like walk flow, and this, I guess these are the capacities and these are the costs. This is like the most expensive arc with respect to cost, and this is the arc that uses the largest fraction of capacity. So let me just say like one word. Okay, so yeah, let me try and do this as quickly as I can. What we're going to do is we're going to start with an arbitrary path, going from S to T, and we're going to try and like modify it so that it fits in this like small class of like really good walks, of which there are a small number. And like how do we do this? We're going to like iteratively modify the path, okay, to make it somehow better or simpler. And the key perspective is the key operation is what we call path patching. So we have like our path from S to T. It has its like most expensive arc, and it's that's the cost bottleneck and the flow bottleneck. And what we're going to try and do to simplify this path or make it better is we're going to replace this subpath in between by essentially the path that maximizes the product of the gain factors going from here to there, that like preserves locally preserves the fact that this is the bottleneck of cost and this is the bottleneck of flow inside the patched segment. So we're going to find the largest gain path such that these two guys remain the cost and flow bottleneck inside this subpath. Okay. And it turns out, I mean, it's not hard to prove that once you do this, like the flow bottleneck will in fact stay the same for the entire path, not just this subpiece, but the cost bottleneck may actually jump to the front. That's the only thing. There are only two things that can happen. So either like, well, this guy won't move. This guy may move in terms of changing identity, but if he moves further to the front. And so what that means is you can sort of keep repeating this process, but you can only repeat it n times because the path starts of length n. And you sort of keep patching and keep patching and keep patching until the process stabilizes. So it'll stabilize once I do a replacement and the cost bottleneck and flow bottleneck don't change. And at every step, like everything is getting better, is basically the perspective. Things are getting cheaper, and I'm using less flow because somehow gains are increasing. Okay. And roughly speaking, this then allows me, at the end, once like the process is stabilized, so it sort of tells me, oh, I did this like, this replacement of like finding the maximum gain path, like in between, the end of this arc and the beginning of this arc, and that didn't change the global signature. That allows me to now like locally define these walks. And the local definition will be like, okay, I take any pair of edges, possibly this way or that way. I find the maximum gain path in between them that like locally preserves signature. Then I need to like extend it to like a global ST path. And I sort of roughly speaking find, the best way of doing it here, which corresponds to another maximum gain path, and the best way of doing it here. You don't have to understand that too deeply, but like roughly speaking, I can recover like the whole walk just using these two arcs. Like there's a local procedure that says like once I know these two arcs, I can in fact recover a whole thing, and because I kind of iteratively did this path patching until the process stabilized, this will give me a set of walks that's better than everything I started with. Okay. And you know, there's a quadratic number of these things, so like that's okay. That's where like that's where m squared would come from. Mn is a small variation on that. So this is like the, you know, a flavor, let's say, of the work that we have to do. And you know, you do a lot more work and you stick paths together in the right way, and you get cycles, and then you get bicycles, and so on and so forth. All right. So in conclusion, we showed that this notion of complexity of central paths for generalized flow is polynomial in just the number of arcs and variables. This also then allows us, because we're doing interior point methods, which are always generally primal-dual, it allows us to solve the dual problem as well in this in a number of iterations that depends on straight line complexity. So we can essentially solve all the related optimization problems. You can ask, and this is something I didn't mention, like maybe, you know, this like fantastic interior point method approach allows you to solve like all linear programs in strongly polynomial time, and the answer is unfortunately no. Mm-hmm. So there are linear programs that have, you know, something like m variables and order m constraints, where you have an exponential lower bound on the straight line complexity. But I do think there is like still a lot of room to play. One thing for people who one thing I want to sort of build a more general, robust theory of straight line complexity. And one nice question that arises, at least from this work, is that we've kind of identified like a class of signed matroids. So that's corresponding to the matrix A, such that sort of any representation of this matroid, which is what you use in the linear program, like yields something that has small straight line complexity, which is a property in this context only of the circuits. Okay, so you could ask, like, are there other like signed matroids such that sort of any representation has small straight line complexity? I think, you know, or like, what's the limit of this? I feel like maybe that's a question that can be answered. And then if you're actually interested in real algorithms, like our interior point method is like ludicrously slow times, you know, this giant polynomial factor that relates to the sum of straight line complexities. So it would be nice to actually find like a faster and possibly simpler algorithm. Okay, so that's it.
Thank you. Any questions? Yes.
So you, at the beginning of your talk, you said that this is essentially like primal-dual algorithm.
Yes.
So, and like the part, yeah, I cannot claim I understood everything, but the part that you understood in the last part of your talk, that also dual algorithm, right? So like a
yeah, I mean, so
algorithm for solving the dual.
yes,
Yeah.
so let's say like our algorithm always will solve the primal and the dual at the same time. So like the dual of minimum cost generalized flow is two variable per inequality linear program. So you know, it's sort of, we solve both at the same time. That was all I wanted to say. So both can be solved in strongly polynomial time. Sort of a geometric version of saying that everything is self-dual is actually, you can kind of look at the straight line complexity of the dual slack associated with the constraint I. And that is, you can prove, is essentially up to a factor of 2 the same as the straight line complexity on the primal side. So even these, at the level of straight line complexities, you have like almost exact duality. That like the corresponding object on the primal has the same complexity as the object on the dual.
Yeah, so for your matroid question, like, the signed matroid, do you mean it's an oriented matroid, or what is a signed matroid?
Yeah, I mean, I don't even know what signed matroids are particularly, but it's basically, you know, you should have, the object should have circuits, and the elements of the circuit should have signs. right? Just
Yeah,
corresponding.
Yeah, that's an oriented
Yes.
matroid, I think.
Yes.
Yeah.
Okay.
I
Oriented.
don't know oriented matroids either, but
Yes. I mean, just corresponding to the fact that things can be positive and negative.
yeah. So you have the support.
Yes.
Then you can also keep track of which coefficients are positive.
Yes.
I think.
Yes. Yes.
When you present this view of all the LP subclasses, and then there are combinatorial LP problems that gives a strongly polynomial time algorithm, but all of those have like integer solutions, right? So the integer programming is also easy, right? In the
Yeah,
list.
I mean, well, for, let's say for like minimum cost flow, I mean, it depends, or even like for maximum flow, it depends on whether your capacities are integer.
Yeah. and
So
assuming-
it's still like, you know, the shortest augmenting path thing, for example, is still strongly polynomial irrespective of the capacities.
Uh-huh.
Right? It doesn't matter if you have
I
like
wonder
root 2.
For your problem, like do we, like one question is, can we do IP as well, or maybe no integer programming?
If you want to do IP with 2 variables for equality, you should ask him. But I mean, there are corresponding results, but they need restrictions. I mean, this was like you need these subdeterminants to be bounded, but like what it essentially ends up boiling down to is whatever maximum weight stable set on graphs of bounded odd cycle packing number. That's like the thing that you end up getting.
And another question is like, so you have this root m log m factor,
Mhm.
right? Because you use this huge machinery.
Mhm.
If you combine the methods of the previous algorithm, can you like eliminate, like reduce this factor?
But the of previously existing algorithms?
No, you're using this interior point
Yes.
method with the SLC bound, but then
Yes.
there's a root m log
Yes.
factor.
Right, this root n thing is kind of like it's a standard kind of bound that says if you have like a, you know, n inequality linear program, then in like root n iterations of like a standard interior point method, the kind of gap
Oh.
divides by 2.
Okay.
Like this is sort of where that root n comes from.
Uh-huh.
It's it's coming from like the standard convergence
So
analysis.
root m is unavoidable, but then the log m.
No. You could potentially use like more sophisticated interior point methods that like can do a bit better.
Uh-huh.
But then like there's the whole question of like how you mesh that with straight line complexity, and it's not clear. Like in the sense that our method has to take very long steps when the path looks very straight. This is essentially you know, straight line complexity is like when is the path straight? You know, there are long segments where the path looks pretty straight, and our interior point method has to like take advantage of that straightness and go faster on these segments. And what happens is that like for fancier interior point methods, we have like less of a clue of like how to interpret straightness, like in like let's say nitty gritty mechanics. And this is why we. I mean, you could potentially improve root n, and it's probably a very good project, but you need a lot of understanding of like the nitty gritty of the interior point methods.
Any other questions? So if not, let's thank the speaker.